Okay, we'll begin with finite fields. My headphones are out of charge, so I am using the laptop microphone. So the audio might not be clear for the first few minutes. While once the headphones are charged for a few minutes, I'll switch to headphones. Then the audio might be clearer. We already know what a field is. A field is a ring in which every non-zero element has an inverse, and we called the elements that have inverses as units in a field. So this is the multiplicative inverse I am talking about. So a field is a ring in which every non-zero element is a unit. A finite field is simply a field containing a finite number of elements. A similar definition is applied to groups and rings also. A finite group is simply a group with a finite number of elements in the set. So a group has a set and an operation, right? So if the set has a finite number of elements, then the group is also called a finite group. Similarly, R has a set and two operations plus and into. If the set R is finite, then we say the ring R is also finite. And we saw examples of finite fields which were Z mod 2Z, Z mod 3Z, Z mod 5Z, etc. Z mod PZ is a finite field for every prime number P. And we denote Z mod PZ by FP. So FP is a field with P elements where P is a prime number. Now before going into construction of finite fields, we will put a restriction on the cardinality of the finite field, that is the number of elements in a finite field. Here we have seen fields with prime number elements. What other number of elements can a field have? There is a restriction on that. If F is a finite field, then the order of F. Order here simply means the cardinality of the set, number of elements in the set. Is the same as what the order of a group was. Then the order of F is Q is equal to P power R. Usually we denote a field by FQ, where Q is the number of elements in the field. Now we are saying Q has to be P power R for some prime P and a positive integer r. So here we saw finite fields where r was 1. So the size was q is equal to p power 1, that is p. Um, those were all z mod pz. Z mod pz gave you finite fields fp whose size was p power 1 for some prime p. There are other ways of constructing fields which can give you, of course this lemma doesn't say it, but if there are other fields other than this z mod pz, then they must have some power of prime number of elements. So you can't have a field with 6 elements because 6 is not a power of any prime. And the proof is as follows. During the ring homomorphism lecture, I showed that from Z to any ring there is only one homomorphism. From Z to Z there is one homomorphism, and from Z to any ring there is only one homomorphism. That was since one had to go to the identity, multiplicative identity in the codomain. Phi of the integer 1 is 1r. There is no choice. Then phi of 0 is 0r, and phi of minus 1 was minus 1r. These were because of the structure of homomorphisms. So then phi of 2 was phi of 1 plus 1, which is phi of 1 plus phi of 1, which is 1r plus 1r. Similarly, phi of n was 1r plus 1r n terms, where n is greater than 0. If it was negative, you would add minus 1r n terms. So just from 1r and the addition in the ring R, what is 1r plus 1r? That will depend on the ring R. But just from that, the homomorphism is completely specified. There is no other flexibility here. These must be the values of phi of 1, phi of 2, phi of 0, phi of minus 1. Every value is fixed. It depends entirely on what is the identity element in the ring R and what is the sum of the identity element added 2 times, 3 times, and so on. That completely decides what is the homomorphism. So there is only one ring homomorphism from Z to any ring. Since every field is also a ring, there is only one homomorphism from Z to the field. So consider the unique ring homomorphism from Z to F.
And what would be the meaning of ring homomorphism? I mean, how does it differ from the normal homomorphism? Does this mean that there is a homomorphism from something to a ring?
It is a homomorphism from one ring to another ring. Group homomorphism is a homomorphism from one group to another group. A group homomorphism is a function such that phi of a plus b is equal to phi of a plus phi of b. This is from one group to another group. A ring homomorphism is a function from one ring to another ring such that phi of a plus b is equal to phi of a plus phi of b. Phi of ab is equal to phi of a into phi of b, and phi of 1 in the ring R is equal to 1 in the ring R prime. So this is a group homomorphism, this is a ring homomorphism.
Yes.
Group homomorphism only takes into consideration addition because there is only one operation in the group. In the group G, this is addition in group G, and here you are adding elements in group G prime because phi of A is some element in G prime and phi of B is also some element in G prime. It's a function from G to G prime, right? So if A is an element of G, phi of A is an element in G prime. So on the right hand side, you are adding two elements in G prime. On the left hand side, you are first adding two elements in G and then taking their function value. This is the
What about
this is called operation preservation. This function preserves the operation addition.
yes? What about the addition? Addition, I mean additive identity. Phi of 0r is equal to 0
That
r.
this condition itself will force phi of 0 r to be equal to 0, phi of
Yes,
0 g to be equal to 0 g prime. So we don't write that separately, but it is true. This
correct.
is forced simply by this phi of a plus b is equal to phi of a plus phi of b. But here, these two conditions do not force this, I think. Even if they do force it, this condition is I don't think these two force this condition. That's why I stated it separately. That phi of 1 must be equal to 1.
And now that we are considering a unique ring homomorphism from G to F, does this mean that since G is a ring and then F is basically a field, and because every field is a ring, and due to this we are considering this homomorphism,
Yes, we are considering the homomorphism between the ring Z and the ring F.
right? Yes.
And we studied in one of the classes that Z is a unique type of ring such that there is only one homomorphism between Z to some ring. Of course, if you consider a different ring, there will be some other homomorphism from Z to F dash. But for each ring, there is only one homomorphism from Z to that ring.
Yes, yes, I agree.
Whereas group homomorphisms, you can have different group homomorphisms from Z to F itself because there are lesser restrictions for the group homomorphism condition. Because phi of 1 does not have to be 1 in a group homomorphism. That condition forces the values in the ring homomorphism and you end up with only one possible ring homomorphism. Now we know that F is a finite field, but Z is an infinite set. So this function cannot be injective. It cannot be one to one. Z has infinite elements. Phi has only finite. So there must be multiple elements that go to one thing. So it's not possible to have a one-to-one function between them. And we already saw in one of the classes that if a ring homomorphism is injective, then the kernel is the zero element set containing only the zero element.
So, and vice versa also was true. If the kernel is, if the kernel contains only the additive identity, then the homomorphism is injective. And if the homomorphism is injective, then the kernel contains only the additive identity 0. Since P is not injective, that means the kernel of P is not simply 0. Then we have, so a lot of the things that I am going to say next, I have not covered due to lack of time. So these things you will just take it at face value for now. You'll just have to believe me. Later, maybe later we'll come back and show these things. So we know Z mod kernel P is isomorphic to a subring of F. So I have not really defined what is Z mod kernel P. Then since F is a next, all these things, if you don't understand, it's okay. We'll come back to it later. Since F is a field, this means F is an integral domain. And if F is an integral domain, then any subring of F is an integral domain. Yes, I already proved that in one of the classes. Yes. If AB is 0, huh? If AB is 0, suppose you say A is not a zero element, then A has an inverse. Since I'm taking consider a field first. Let's say in the field A into B is 0. Suppose A is not the zero element. Then A has an inverse. Then you can multiply on both sides by the inverse. You will get B is equal to 0. So if you have A into B is 0 and one of them is not 0, the other has to be 0, which is exactly the condition for integral domain. Yes, because of inverses, it is not possible to have two non-zero elements that give you 0. But this is not the case for a general ring, right? The element A might not have an inverse, so you can't do this. So it is possible for A and B to be non-zero elements, but their product to be equal to 0 in a in simply a ring. So every field is an integral domain. But if the product of two non-zero elements is 0 in a set, if you take a smaller subset of it, then that condition holds in the subset also, right? You simply pick a fewer elements in that field. Then suddenly the product of two elements can't be 0. Two zero non-zero elements can't be 0, right? In a subset. So any subring is also a subset of the field with made to have additional properties, but it's a subset of the field itself. So the product of any two elements there also can't be 0 without one of them being 0. So a subring of the field is also an integral domain. Now the next part I have not explained, but um, this red mod kernel phi is isomorphic to subring of f, right? So this isomorphism preserves all the properties of sets and fields and groups. So in on one side, if the so whatever subring of f this is, since that is an integral domain, the Z mod kernel phi will also be an integral domain. So if this subring of f is a field, then Z mod kernel phi will also have to be a field. So if there is an isomorphism between two rings, then whatever properties are held by one ring, the same properties will be held by the other ring also. Explain what. Here we are using ring properties. That's why. Z mod kernel phi is not a field. Z mod kernel phi will be a ring. So it is only isomorphic in the sense of a ring to a subring of f. If it was isomorphic to a subfield of f, then Z mod kernel phi would also have to be a field. In general, that is true. Yeah. Yes, yes, I had explained cosets, right? The yes, yes, yes. This is simply cosets of the kernel, the set of cosets of the kernel. So the mod kernel phi is kernel phi, some element in Z plus kernel phi, some other element in Z plus kernel phi, etc. But depending on homomorph what the field F is, that will give a particular structure to phi. Depending on that, uh, that will show there will be whatever size of F is, there will be that many sets here, unique sets. Rest of the sets will overlap with one of these. This will go to some element. Yes. So there will be cardinality of F mutually exclusive cosets. And any other coset would simply be one of these cosets itself. It will completely overlap. So this will form a group if you define addition properly. This will form a ring. We define addition and multiplication properly. That is, we will define it. So this would give you a ring, right? This ring is isomorphic to some subset of the field F, subring of the field F. That is because each element in this coset goes to under the function phi will go to the same image. Let's say the field elements are alpha 1, alpha 2. And this will all this kernel is a set, right? The set of elements that go to 0 in the field. So all kernel elements go to the element 0 under F under phi. That is clear, right? So similarly, uh, all the because of the special property of the kernel phi, this doesn't happen with any random set. You can't take Z mod some random set in subset of Z and do this. This only works for kernel phi. Then this kernel phi goes to 0. All the elements in A plus kernel phi will go to some element alpha A. All the elements in B plus kernel phi will go to some element alpha B, etc. Go to alpha E. These are field elements. So for every field element, there is a set of elements that will be mapped onto that element, right? And that set of element will simply be one of the cosets of the kernel. So in that sense, if you have this domain here and the field, let's say it has three elements, 0, alpha 1, alpha 2, like this, then you can split this. This will be kernel P. All these elements go to 0. Then this will be kernel P plus 1, let's say. All these elements go to alpha 1. This will be kernel P plus 2. All these elements go to alpha 2. So you can split the domain into partitions so that there are exactly cardinality of f number of partitions. So if this entire three set of three elements you consider one block, let's say, then that block is associated with 0. Then this entire set is considered one block, then that block is associated with alpha 1. This is associated with alpha 2. Now this is a bijection, right? For each field element, there is one block that is going to that field element. And for each block, there is one field element. So it's a bijective function. So it is an isomorphism. Isomorphism is simply an operation preserving function that is also bijective. Now, I haven't shown you the operation preservation. That is, I also have to show that phi of block 1 plus block 2 will be equal to phi of block 1, that is 0, plus phi of block 2, that is alpha 1. and phi of block 1 into block 2 is equal to phi of block 1, that is 0 into phi of block 2, alpha 1. So I haven't shown that, but that will also be true. On top of that, it is also it is also a bijective function, so it is an isomorphism. So this kind of isomorphism exists between Z mod kernel P and the field F, not the field F, some subring of the field F. So F is a field, that means F is an integral domain, which means as any subring of F is an integral domain, which means the set that is isomorphic to the subring because of isomorphism, that set is also an integral domain. That is kernel Z mod kernel P is and this is very simple. Yeah. Why is this the case? If you have one set A here and another set, let's say you have numbers here and you have letters here, A, B, 1, 2, and there's a bijective isomorphism like this from phi. Suppose phi of A into phi of B is 0. That is, this must be phi of 0. You know phi of 0 is 0, right? That would mean phi of AB is equal to phi of 0 because of the homomorphism property. But since phi is a bijective function, phi of AB is equal to phi of 0 would mean that AB is equal to 0. So whenever the reverse direction also holds. So whenever A into B is 0, the pre-image 1 into 2 must also be 0. And whenever 1 into 2 is 0, the image A into B must also be 0. Furthermore, 0 is equal to phi of 0. There is only one image for 0. The 0 here must be mapped to the 0 here. So this will force the condition that if A into B is 0 here means that A must be 0 or B must be 0. Then if 1 into 2 is 0 here, then 1 must be 0 or 2 must be 0. It will force that condition. So any type of condition that holds in one side will also hold in the other side. Because you can simply use this bijective mapping to go from one side to the other. And that bijective mapping also operation preserving. So if one side is an integral domain, the other side must also be an integral domain. So Z mod kernel P is an integral domain. So once Z mod for any ideal I and a ring R, if R mod I is an integral domain, then that ideal has to be a prime ideal. I have not defined what that is. So this will simply imply that kernel P is a prime ideal. All ideals of Z are of the form NZ. We have seen that. All ideals of all prime ideals of Z are of the form PZ for some prime P. So since kernel P is a prime ideal, this would imply kernel P is PZ for some prime P. This would imply Z mod kernel P equals Z mod PZ for prime P is a field. So this Z mod kernel P that I took to be a ring initially, we didn't know whether it was a field or not. It turns out that that has to be a field. So this subring of F that I was talking about, which is isomorphic to Z mod kernel P, is actually a subfield of F. So F is here and you have Z mod PZ within this F, which is a subfield of F. Of course, it's not directly. There is some set F prime, which is isomorphic to Z mod PZ. So this is FP, F, this is F, F dash, which is a subset of subring of F that is isomorphic to Z mod PZ, which is a subfield. So F prime is some subfield of F containing P elements. So that also this is a finite field. So F is a finite field, F prime is a finite field. Now there is something called the degree of the field extension. Let's say it is R. So if R is the degree of field extension and F prime has P elements, then F will have cardinality of F is P power R. Isomorphic to a subring of F. That I have not explained these things. You'll just have to take it at face value for now. Yeah. No, no, that is an entirely different thing. That would mean an R length vector containing elements from Fp. Each element is from Fp. Like R3, if you write a superscript, that's a three length vector, right? From with elements from R. So FPR would become an R length vector with elements from F. You can write Q is equal to P power R and then call it FQ. That's what is mostly done. Or if you really want to do it, you can write FP power R. But most of the time, you simply call Q is equal to P power R and then call it as FQ. FQ is standard notation for field of size Q. So yeah, here many notions I have not explained. First is that why is red mod kernel phi isomorphic to a subring of F? That I have not really proven. I showed it to you in kind of a vague example, but I did not prove it. Then I did not define a prime ideal. I have not defined a prime ideal. I also have not told you why Z mod if Z mod kernel P is an integral domain, then kernel phi must be a prime ideal. I also told not shown you that if kernel phi is a prime ideal of Z, then it must be of the form pz for a prime number. And lastly, I also not explained what is the degree of field extension and why if f prime has p elements and f is an extension field of degree r, f has p power r elements. I have not explained any of these notions. I'll explain all these notions later. I'll explain to you at least this notion of the degree of field extension. First of all, we'll go in a systematic way, even though this is simply very brief, not detailed. So F is a field if it is a ring such that F minus the zero element is a group under multiplication. So a ring already has all the properties to make it a group under multiplication except for the inverses. So if you remove 0 and say that all the non-zero elements have inverses, multiplicative inverses, then f minus 0 will be a group. It's the same as saying that all non-zero elements have multiplicative inverses. Then let K be a field, a subfield f of K is a subset such that f is a subgroup. F is an additive subgroup of K, and f minus 0 is a multiplicative subgroup of K minus 0. So in the sense F is also a field, that's all. But it is a subset of K. And one thing to note here when you say it is a subfield or a subring, right? The operation is the same. So whatever operation K has, the same operation you're using to say that F is a subgroup of K and F minus 0 subgroup of K. The addition and multiplication there is the same. So in that sense, the set Zn is not a subgroup of Z, even though Zn is a group. Z is a group. Even though we write Zn to be elements 0, 1, 2 up to n minus 1, which is a subset of Z. But Zn is not a subgroup of Z because the operation in Z is simply addition. But the operation in Zn is modular addition. The operation is different in those two groups. That's why those two can't be subgroups. Yes. Second condition is totally different, no? Ideal. It has nothing to do with inverses. Second condition is simply that if A is in the ideal and R is any ring element, RA must be in the ideal. Such a condition is not here. Here, the second condition is that yes, and here it must f minus 0 must be a multiplicative subgroup. That is not a condition for an ideal. So at the end of the day, F is a subfield of K if under the operations of K, F is a field and F is a subset of K. Then next thing is that if F is a subfield of K, we say that K is a field extension or extension field of F. We write K by F is a field extension. Or you can also write K superset of F, or F is a subset of K, or K with a dash and F is a field extension. So field extension is two fields in which one is a subfield of the other. Yes. Only fields we call them field extensions. Blueprint things we don't have that kind of name. Then Let K by F be a field extension. We can consider K as a vector space over F. The degree of K over F, the degree of extension, is the dimension of K as an F vector space. In symbols, that would be, you would write degree of K over F is the dimension of K as an F vector space. Huh? You have not studied vector spaces? You know the uh, algebraic formal definition, or you know it simply normal math level? I can't write down the formal definition off the top of my head, but I can tell you a little informally. So a vector space is set V, a field F, addition and scalar multiplication. So these are the things that make up the vector space. The elements of the set V are called vectors. For example, R3, R plus and dot, where R3 is the set of 3 by 1 vectors, three dimension vectors, 1 to 3. Set of such vectors is R3. Elements of the first set V are called the vectors. It is a set of vectors. This is a field. This is a field of scalars. When we are dealing with real numbers, the scalar field is real numbers. This operation plus is an operation between the vectors, whereas V plus is an abelian group. That you can see, right? The addition here would be 1 to 3 plus 4 5 6 is 1 plus 4 5, 2 plus 5 7, 3 plus 6 9. So under that operation, R3 is an abelian group under addition. Then dot is closed. I mean, the set is V is closed under scalar multiplication. That is, if you take some element in R, that field of scalars, here it is R in the example. So let's say 3, and you multiply that with a vector in V, that is R3 here, 1, 2, 3. What you get is 3, 6, 9, which is also a vector in R3. So if you take some element in F and multiply it, scalar multiplication. So this is not, F and V are different sets, right? So the multiplication is not a binary operation. Binary operation was between elements within the same set. Here, F is a field of scalars, V is a set of vectors. So this dot is an operation with one element in F and another element in V. So even then, it must be closed in the sense that the product of a scalar with a vector must be a vector. So here in our real number example, 3 into 1 to 3 is 369, which is also a vector in R3. Then additional properties are distributive properties. So we have two scalars, alpha 1 and alpha 2 into a vector V. This is the notation we'll use for a vector. We'll underline it. This must be equal to alpha 1 dot alpha 2 into vector V. And alpha 1 vector V plus alpha 2 vector V is equal to alpha 1 plus alpha 2 dot vector V. Finally, last property is that 1 dot vector V must be equal to vector V. These all hold in the example also. 2 into 3 times 1 to 3, which is 6 times 1 to 3, is 6, 12, 18. But 2 into 3 times 1 to 3 is 2 times 369, which is 6, 12, 18. Distributive property is important. Yes, they must have the property. They are scalars. Alpha 1, alpha 2 belong to F and vector V belongs to set V. Subspace is again a subset of the vector space, which is a vector space itself under the same addition and scalar multiplication with the same field. Most of these subgroup, subring, subspace, everything is that they are subsets of the original set which form the same group structure, the same algebraic structure. That is a subset of a group which is also a group, a subset of a ring which is also a ring, subset of a field which is also a field. Here, subset of a vector space which is also a vector space. With the condition that it is a group under the same operations as the superset. You can't have a different operation. Can't pick a subset and then change the operation and say that this subset is a group under this different operation, so it must be a subgroup. No. Whatever operation the group has under that same operations, so in terms of vector space under the same scalar field f and scalar multiplication and addition. Under the same operations, the subset should also have that same algebraic structure. So this is how we define vector space in algebra formally. Yes. Yes, you can do it. You can find a basis for V, and then once you have a basis for V, each vector in V is some linear combination of the basis vectors, right? So then you can write that linear combination as a set of as a vector containing elements from F. So if you have set V plus F plus dot, then some basis you have B1, B2, B3, Bn. Consider the finite case. Then each vector in V is of the form alpha 1 B1 plus alpha 2 B2, etc. Alpha n Bn, where alphas are elements of F. So it's a scalar linear combination. So the coefficients are from F. So every vector in V can be expressed in this form using the basis vectors, right? Then you can simply remove this B1, B2 and the additional symbols and write alpha 1, alpha 2, etc. to denote this sum. It is very clear, right? There is no confusion. Once the basis vectors are specified, you can simply give the and you give an arrangement for the basis vectors. You give an ordering for the basis vectors, B1, B2, Bn. Then you can simply put the coefficients as a vector. That is basis vectors will take care of that. Yes, 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 yes. Once you fix the set of basis vectors, then you can simply specify each vector by a list of scalars, alpha 1 up to alpha n. This is clear, right? So you can do this for k over f. Consider V, you have k over f, the field extension. So k has plus and into, f has plus and into, and f is a subset of k. Consider the v plus f dot. Consider k is equal to v, this plus is this addition, this dot is this multiplication, this f is this f. Then it's k over f, k is actually a vector space over f with a field f. Is that clear to you? See, directions, actually vector has nothing to do with directions. That's only for our understanding and for application in physics. Vector is a mathematical tool which is defined this way where nowhere I have called directions at all. So in our case, right, this vector can be a signal and a set of all finite length signals. A set of all signals can be our vector space, and you can get a basis using cosine and sine signals using the cosine transform or the Fourier transform. So whereas there's no direction for a signal, that we are trying to understand with the example. That's vector space in that's how it works, right? Group there is no there are only properties, and whatever set follows has that property is a group. Similarly, whatever set V and F plus and dot have this property, that's a vector space. The definition of a vector space doesn't give you an example or a construction method to give you vectors or vector space. It's the opposite direction. So it. For example, we looked at integers. We thought it had nice properties, so we said we would like to study all structures which have similar properties to integers without bothering about the fact that it is a set of integers. In general, if these nice properties are there for some set, what can I say about that set? How can I use it? Without every time going back to the fact that it is a set of integers. Then for set of integers, I'll have some algebra. Then for the set of matrices, I'll have some algebra. For each of them independently, you have the fields which study them exclusively. But abstract algebra would like to study them as structures without looking at the specifics. You only look at the specifics when you want a particular problem or an example. So you took out the properties, nice properties that are there in integers and said that any structure that has those properties is called a ring. Then we found out that there are other rings, polynomial rings, that have nothing to do with integers. But their properties are also, a lot of the properties overlap between rings and polynomial rings, or between integers and polynomial rings. For example, Z mod kernel phi is a isomorphic to a subring of the codomain. That property doesn't really, so it need not have been Z. For any, if there was a homomorphism phi from uh, G to G prime, if there's a group homomorphism, then G mod kernel phi is isomorphic to a subgroup of G prime. So that does not depend on what G is, what G prime is, and what the homomorphism phi is. It will always be true. Then when you need an application or an example, you go to specific groups and find out what the kernel is in that specific example, find out what Gmod kernel phi is, etc. That's the case here also. We define a vector space to be a set V. It's a set that is enough for us. It's a set and F is a field. Plus and dot are operations. Plus is between two elements in the set, binary operation between two elements in the set, and dot relation operation between an element of F and an element of V. It has these properties. There are usually you expand instead of simply abelian group, you expand that also and you write seven properties, seven or eight properties. That would be called a vector space. Then the set of real number vectors, complex vectors and all will also be vector spaces according to our definition. But there are other vector spaces which have nothing to do with R3. For example, this field vector space, it has nothing to do with this kind of does not have an analog in real numbers, right? R plus R dot is a vector space, doesn't make any sense, right? But it does make sense when you look at a field and its subfield. You can always write a field as a vector space over its subfield. This part is clear, right? And it's a subfield. Uh, uh, if it's a subfield, then you can consider k plus f dot, k plus f into as a vector space over f. You can consider k as a vector space over f. That is k plus f into is a vector space. For example, I'll give you an example that will make it clear. Uh, Consider k is equal to set of complex numbers. F is the set of real numbers. Both are fields and R is a subset of complex numbers, and the addition and multiplication in R is the same as addition and multiplication in C, right? Except that the imaginary part is always zero in every number of R. So you can write every real number as, let's say A is a real number, you can write it as A plus 0I. So that would be an element of the complex numbers. So in that sense, R is a subset of C. But R is also a field, C is a field, so R is a subfield of C. Okay, I'll finish with this example. Um, Now you can write C plus R dot is a vector space. How can you write that? That is because consider 1 and I in C. Every complex number is A plus IB, where A comma B belong to R. So you see, this is like we have 1 and I, these are two vectors, and you multiply with them with scalars in the scalar field, and you add them. So you're taking scalar linear combinations of 1 and I with the scalars from the scalar field R. So it is a vector space, right? With the basis 1 comma I. So in the same way, for any general field K with subfield F, you can always find a set of elements in K to form the basis. And to get any element in K, you simply multiply the elements of F, which are also actually elements of K itself. Just fewer elements are there in F. Multiply it with elements of K with the basis elements of K. Worst case scenario, you can simply take the basis to be the entire set K. Then the product of any scalar with subvec subvec the F is a field of scalar, so one will be in F. One times any field element in K is the field element itself. So in the worst case scenario, you can simply consider K to be the basis. But in most cases, it can be smaller thing. So in that sense, K is a vector space or the field F. Then once you have this, is a vector space, you have that there is a basis for K, and such that every element in K can be written as a linear combination, scalar linear combination with scalars from F. Then the size of the basis is the dimension, right? So that is called the degree of K over F when it comes to fields. K and F are fields. F is a subfield of K. Then if you consider K plus F dot F into as a vector space of elements from K over the scalars from F, then if you find a basis for K, the size of the basis will be the dimension of K. That is called the degree of K over F. So here whatever I had used, here R, this is the degree of F over this ZP. And from vector spaces, you know that if there are if there are P scalars and R basis vectors, then you can have P power R elements in the vector space. Okay, we'll end with that. Next class, I'll show you the construction of finite fields of these sizes, and we'll be done with the course. We'll have one tomorrow. What time you want?